In this video, we're going to look at what happens when you combine multiple springs together in either series or parallel, and we talk about the effective or total spring constant that results in. We are going to think of a system of springs as if it could be replaced with a single spring and find out what that spring constant K would be. So if you imagine taking two rubber bands and when they're parallel to each other, two linked around the same thing, and you pull, is the effective spring constant larger, small, or smaller than K would be individually. Similarly, if you put two rubber bands in series, one after another, and pull on it, which would be larger or smaller. Now, this is something you could easily do at home if you have some rubber bands lying around, and you can try it. But the thing we're looking for here is which is harder, right? Which ends up being a stiffer spring. It turns out that we can actually figure out how this behaves by looking at Newton's laws and what we know about the spring force. So if we have springs in series, one after another, right? If you let a mass pull down on this spring, right, each spring will stretch some amount, right? And the force throughout, assuming these are ideal springs, will be the same everywhere, right? So we have one force with two different stretch distances. And so what we can do is we say, well, our effective spring constant is the force that is being applied divided by the total stretch distance. And that means x1 has its force divided by spring constant 1. x2 is the force divided by spring constant 2. And this just comes from the definition of the spring force. And so if we flip the equation around and kind of put it all together, we can cancel out that force, and we end up with K effective, or the amount of spring constant we have for the whole system, as if it were one spring, is actually the sum of the 1 over the K effective is the sum of the inverses of the spring constants. Right? So for in series, we add up the inverses or the reciprocals of the spring constants, and then we take the reciprocal again. And this is because we have one force, but much bigger stretch, the same force we would have with one spring, but much bigger stretch. And if it stretches more with a given force, that's a smaller spring constant. And you probably know that when you add a bunch of reciprocals and take the reciprocal, you get a smaller number than either of the original values. If we talk about in parallel here, try to get that out of the way, or in series, again, and we do a little example. Here's spring constant 1, 30 newtons per meter, spring constant 2, 20 newtons per meter. If they are connected as shown like this, what is the effective spring constant? Well, that's 1 over 30 plus 1 over 20, which is 5/60ths. And then the K effective is about 12 newtons per meter. Notice that this is smaller than either 20 newtons per meter or 30 newtons per meter. Right? Springs in series are weaker. That's the big takeaway from this. What about springs in parallel? Well, when springs are in parallel, right, the force that each of them provides can be different, but they have to stretch the same amount, right? You can't stretch spring 1 without also stretching spring 2 in this case, but each one of them will provide some of the force. So K effective is still F total divided by some stretch distance, but that F total is the sum of the two forces. And of course, each spring force is Kx for its individual value. The x's cancel out, and we end up with K effective is equal to the sum of the spring constants. So when you add them in parallel, right, you get just a bigger spring constant than you would for individual springs. An example of that one, K1 and K2, you apply a force here. What is the effective spring constant? These are, again, the 30 Newton per meter and the 20 Newton per meter spring constant. We simply add them together for 50 newtons per meter. Springs in parallel are stiffer or harder to pull, have a bigger spring constant than an individual spring. So, in summary, when we're adding in series, 1 over K effective equals the sum of the reciprocals of every individual spring, and in parallel, K effective is the direct sum. These are also on your equation sheet, but they're not written quite in the same way. They're the exact same thing as what we would do when we add capacitors, but that's not until the spring when we get into electricity and magnetism. What if we have springs that are in series and in parallel, what we would call a compound arrangement. Well, for this, we just have to take each segment in turn, right? Springs 1 and 2 are in parallel with each other, and then if we were to replace that with an effective spring constant, that spring would be in series with spring 3. So all 3 springs have the same spring constant for simplicity here. Where do we start? Well, we start by adding springs 1 and 2, which gives us 140 newtons per meter. And then we add spring 3. That's now adding as reciprocals because it's in series. We flip it and we end up with 47 newtons per meter. So we have a spring constant that is less than either 3 or the combination of 1 and 2, which is 47 newtons per meter. Another example. So you have a 1 meter long spring, has a spring constant of 70 newtons per meter. You cut it in half. What is the spring constant of each piece? Now, this is kind of an interesting result. The original spring is like 2 springs in series, right? And if you were to reconnect the 2 halves and use it, that's what it would be. So we could say, well, the long is basically 1 over the spring constant of the long is equal to the sum of the reciprocals of the spring constants of the shorts. So 1 over k long is equal to 2 over k short. We can flip that, my video out of the way, and we find out that k short is 2 times k long, right? Because when you add them in series, you get a smaller spring constant as a result. So we get 140 newtons per meter. Short springs are stiffer than the long spring in the same construction. Basically, hopefully this makes a little bit of sense because it's harder to stretch these short springs the same distance that you would the long spring. So what about spring constant of a 20 centimeter long piece? Instead of splitting it into halves, how do we do this? Well, think about what happens. If a 100 centimeter spring, 70 newtons stretches it 1 meter, right? That's what it means to have a 70 newtons per meter spring constant. A 20 centimeter piece, 70 newtons should stretch it 20/100ths of a meter, right? Because the amount of stretch is split up evenly over the different parts of the spring. And so the spring constant final, since the force is the same everywhere along a series configuration, we can find the new stretch distance, which is 20/100 of that 1 meter, gives us 350 newtons for the spring constant of that segment. That's it. It's pretty straightforward. We need a little practice to get used to it, and that's what we'll be doing in class.